All right. In these questions, it talks about classifying polynomials. So the first thing that we're going to be asked is whether or not what we're looking at is a polynomial. Now, polynomials are defined by having whole number exponents or degrees. Now, a whole number, let's talk about that for a minute, is all the natural numbers plus the value of 0. So basically 0, 1, 2, 3, dot, dot, dot. So no fractions, no negatives, no irrationals is what a whole number is. So if you look here and you see a 5, and you look here and you see nothing, that nothing is actually a 1 because it's a variable to a power. These are whole numbers. So the first thing that we do is we say that is indeed a polynomial. So we say, yes, it represents a polynomial. Then it has a follow-up question. We're not done. There's more. That's because there's so much more to polynomials. Well, the next thought is, what is the degree of the polynomial? The degree is the highest exponent present. Now, or the highest exponent present, there's actually more to it if there was a product happening. All of our examples are going to have single variable to a power. Technically, the degree could be the result of multiplying two bases and you add the exponent. But we're going to talk about the highest exponent present. That'll suffice for the polynomials that we're looking at here. So we look at this one and we see the 5 is the highest one. So we just say the polynomial is a, and then there's names based on the highest degree. So let's go ahead and get a list of names. You see a few of these, and then it has a degree of whatever. Actually, this one just asks for a degree of 5. The polynomial this is based on how many terms you have. So we classify by terms and numbers of powers. So let's give a list of term names. Now, terms are individual connected product values that are separated by addition or subtraction. If there's an addition or subtraction sign, you've separated terms. So there are exactly two terms, one term, two terms. So terms are separated by addition or subtraction. Okay. And so terms, the number of terms classify. So if there are two terms, we call it a binomial. If there are three terms, we call it a trinomial. If there are 4 or more terms, we call it a that many term polynomial. We have no more special names for classifying by term. I mean, we have more names in geometry for higher values than 3, but here we're sticking with binomial or trinomial. Now, I didn't give us 1. If we have just one term, it's called a monomial. So I'm going to go up with that one. Sorry, I didn't write that first. If you have one term, it's called a monomial. Mono for 1. Now, the degree here, we're just going to name it, but we do also call different powers, different degrees. I'm going to write that right here, starting with 0 degree. If the degree is 0, it's called a constant. If the degree is 1, it's called linear. You should be very familiar with these names. The degree is 2, it's a quadratic. The degree is 3, it's a cubic. The degree is 4, it's a quartic. And if the degree is 5, it's a quintic. After degree 5, we just call it a 6 or more, whatever it is. Polynomial of degree. Actually, I put that the wrong way. It's just you say polynomial of degree. So this is just whatever the degree is. So we don't come up with a special name for 6, 7, 8, and so on. So we're going to make sure we do have that list, even though this problem isn't going to require it. So have this list somewhere special for the names there, and then somewhere special for the names of the terms, naming by terms. All right, so now clicking through in this problem, the polynomial we had 2 terms. So we're going to call it a binomial. And then the degree we said was 5. And then that was it for this problem. So there's more classification by name that we could do, and in other contexts we will, but for now, that was it. Let's take a look at another example. Holding on to these notes, I'm not going to rewrite all these. We're going to just roll through other examples with these notes in the background on our paper. So in this second example, what throws students typically is that we've got a fraction. And so our brain says, oh, you said only whole numbers. Well, that's for the exponents. If you look at the exponent's a 3. That one's fine. And on the C right here, there's a 1. So we have a degree of 3, degree of 1. This one's fine. There's a negative 1/10 coefficient. That's fine. That does not affect whether or not it's a polynomial. So this is a polynomial. So we click it represents. And then we have a follow-up question. This polynomial is and now we're classifying by terms. There is 2 terms separated by an addition sign. So we say it's a binomial. And then it has a degree of, the highest exponent is 3. On this example, we have a negative a to the negative 5th power. Now, I said we can only have whole number degrees. And now what that looks like, it looks like 0, 1, 2, etc. for whole number exponents. That is a negative 5. We cannot include the list of values left of 0. So immediately we say this is not a polynomial. Or do we? Remember, we had this exponent property that said if you have a negative exponent, you can just make it a 1 over a to the positive 5 power. Ooh, does it make it a polynomial now? No, this is still not a polynomial, because if you wrote it this way, we'd actually want to rewrite it back the way we were given this problem originally to get a negative a to the negative 5th power. We want to look at it, no fraction, no variables down below the fraction. This is actually a rational number, not a polynomial. So we need to look at our variables above the fraction bar, what kind of exponent we have. That's a negative. And so we say not a polynomial because it is a negative degree. So we click not a polynomial. And then we don't have any subsequent questions because we're not dealing with rational numbers in this section. That's for our next unit of study. And now we look at the value negative 2. And most of my students look at that and say, nope, not a polynomial, because there's no variable. That wasn't the question. The question was, does it have a whole number degree? Polynomial or not is just asking if it has a whole number degree. Negative 2 has a variable that you can't see. It's invisible. It's the value of 1. 1 can be replaced with x to the 0 power because x to the 0 power is 1. So actually, this lack of a variable is a constant term. It has no variable next to it. The degree is 0. That's a whole number. 0 is a whole number. So we are looking at a polynomial. So we go ahead and click represents a polynomial. And this polynomial has only one term. There's no plus sign and a separate term after it. There's a minus sign, but there's no extra term. So it's a monomial, and the degree is 0 because it's a constant term. A constant height of negative 2 would be a horizontal line, actually, if we were to draw it. Now, in this problem, we've got a lot going on. We've got some square roots happening. Now, we've got to be very careful about square roots. Square roots might be okay. Let's look one term at a time. First of all, let's classify that there are actually 3 terms here. There are separated. There's separation here by that negative sign and this plus sign. So there's 3 terms. So this is a trinomial. The issue is whether or not it is a polynomial. So So let's look at these one at a time. This a has a 1 exponent. This a has a 2 exponent. The square root of 5 is not in the exponent. It's actually part of the coefficient. I know it's in the back. It's really like a negative 10 square root of 5 and then times by a squared is another way to rewrite this term. So far, the first term is fine. Second term, fine. Those can qualify as polynomials. But then we get to this last term, and we've got this 8 square root of a. Well, what kind of power do we have on the a? Well, there's a 1 inside there, right? And so people click it and they say, oh yeah, it's a polynomial. No, it's actually needing to be rewritten. A square root is actually a 1/2 power. So this square root causes this to not be a polynomial because it is a fraction. That's a rational number, not a whole number exponent. So we go ahead and click in there that it is not a polynomial. Now for subsequent problems, you might see something like a cube root of a, and that would be a a to the 1/3 power. Just in case you weren't seeing your radicals before, this is, say you had a base a, and then this was m, and then you had an n power. There's this property that says any radical can be rewritten as a fraction exponent like this. So in subsequent problems, if you ever have a square root or any sort of root, you can rewrite it as a fraction exponent. Immediately, if you see a radical over top of your variable that doesn't reduce down and doesn't clean up. So say you had a square root, and so here's another trick. If you had a square root of a squared, that's actually an a. So this would be a polynomial. So be careful to just not throw every radical out. You can simplify some, but in this particular context, this problem, we were left with a non-simplifiable radical. So this was not a polynomial. I'd make sure I have this ready to go in subsequent problems. Now, I might have already given away the story for this one earlier. Notice you've got a c to the 5th down on the bottom. Well, we don't actually analyze with our variables on the bottom. We need our variables to be on the top to analyze whether or not it's a polynomial or not. This should be rewritten, 6 over c to the 5th can be rewritten as 6c to the negative 5. If our variable is above the fraction bar, that's when we make our analysis as to whether or not this is a whole number. And immediately we should recognize that's negative. Whole numbers have to be 0 or positive integer values. And so this is not a polynomial. It's actually a rational number. Anytime we're dividing by a variable like that, it's a rational number. So the answer for this one was not a polynomial. We'll look a lot at this type of question coming up in our next unit of study.